Now that we've gotten our ideas of average velocity, instantaneous velocity, and speed, kind of how fast are things moving, sometimes in what direction also, we're going to look at this other quantity called acceleration. And, you know, if you've ever been in a car or moving vehicle of some sort, cars, boats, planes, trains, you've experienced acceleration. If you press on the gas pedal, you're going to accelerate. You can check your acceleration on an accelerometer in a car. So acceleration is a measurement of a change in velocity. So change in velocity over time. Now you could find an average acceleration if you got the velocity at two different points in time and averaged that out over how long of a time was elapsed there. But most of the time we're going to be looking at an instantaneous acceleration. So acceleration being the change in velocity over time, I'm going to make a new function here, a of t, a for acceleration. And this is going to be instantaneous change in velocity over time. So that is the derivative of velocity with respect to time, dv dt. Okay. Now, if we wanted to write that in terms of our original position function, everything going back to that, okay, position s was a function of t, okay, and then velocity was the first derivative of that position function. Acceleration is going to be the second derivative of that position function. So this is the derivative with respect to t of ds dt, okay? Because ds dt is the velocity, and we want to take the derivative of that again. And so the notation for that, remember in Leibniz form, this looks like d squared s over dt squared. Okay. You could also write this as the second derivative of the position function f. So you could write it as f double prime of t. But all of those mean the exact same thing. That's why these problems can get a little tricky sometimes. There are so many different notations to keep track of. But just remember, try and keep track. Position is original, velocity is first derivative, acceleration is second derivative here. Now, if you need it, because some problems you might, we do have certain acceleration constants that will come in handy sometimes. Acceleration, it's the acceleration due to Earth's gravity, because that's a constant that affects all of us all the time, every day, 24/7, 365, because we're all on Earth. Okay, so acceleration due to Earth's gravity is going to be approximately 32 feet per second squared. That's our units, feet per second squared there. Or if you're doing a problem in the metric system, you could use 9.8 meters per second squared. Okay, those are good to know. If you came across that on a test or something like that, I would provide this constant for you. I don't expect you to have that memorized, but you might need to have it memorized for a physics class. So just be aware that that's what we're looking at. All right, so we have a constant acceleration due to gravity here on Earth. But in general, acceleration is just the second derivative of position. Okay, now on to our last quantity for objects in motion here. This one is called jerk. And this is a funny quantity. I like this one. Jerk is a change in acceleration over time. Okay, and kind of a funny way that I like to remember this one is to picture that you are on a bus. This is a really great drawing of a bus, y'all. I hope you appreciate it. And the bus is going along with a nice constant speed. Maybe you don't have any acceleration at first. Here's the little bus driver. There we go. In a little hat. So let's say you're traveling along with a no acceleration or a nice constant acceleration. You're moving forward, and then the bus driver suddenly decelerates. And he does that by slamming on the brakes. Okay. So slam on the brakes, there's a sudden change in acceleration. All of a sudden, you're accelerating way less than you were. And everybody on the bus goes, whoa, what is going on there? Why did you change acceleration so quickly? You know, they say it just like that. Why did you change acceleration on us? And so if there's a big change in acceleration like that, you might call that bus driver a big jerk. Big jerk. So there's the rationale. That's how I remember what jerk is. It's change in acceleration over time. And so we're going to call this J of t. And it's a change in acceleration over time. And we'll look at this instantaneously. So that's going to be a derivative of acceleration with respect to time, dA dt. All right. So that is going to be, well, let's write in a variety of notations here. We could write it in Newton notation. We're just going to take another derivative after acceleration. So this is going to be f triple prime of t, the third derivative. Or you could write this as the derivative with respect to t of another expression for acceleration. Let's do this one to relate back to position here. So the derivative with respect to t of d squared s over dt squared, d squared s over dt squared, which in Leibniz notation would look like this, d cubed s over dt cubed. Okay, both of those mean exactly the same thing. Remember, one's just Newton, the other is Leibniz. All right. You could also write this as, let's see, you could do the second derivative of velocity. We don't tend to do that too much. I think these would be the main notations you would tend to use here. Okay. So that is the jerk. And those are our quantities for objects in motion.